Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we talked about how different circuit elements we have when AC alternating power source is applied across them. So we saw how individual element, capacitor, inductor and resistors we have, and we saw that like here behavior is different from simple or like DC circuits. So we can't simply go for the AC part also exactly the way we used to do in case of DC. So here we have another approach, and that is basically your phasor diagram approach. It helps us a lot in solving problem based on AC circuits or AC like supply AC current and voltage source. And like we talked about like LR circuits, and like how like we current, instantaneous voltage, we can get their relations applying KVL and KCL in case of series LR circuit. So when and in what way we need to apply that. Let's see one simple application before going for the next part on based on LR circuit. So here we are provided with one problem in an LR series circuit. So it's exactly based on the part that we discussed in the last lecture. So in an LR series circuit, so it's a, let me keep writing it simultaneously. So it's LR series circuit, right? This, and this is V equal to V naught sine of omega t. Okay, and it's here mentioned L is equal to 35 millihenry, R is equal to 11 ohm, and frequency is also given 50 hertz, and VRMS is 220 volts. This implies V naught is equal to VRMS root 2 times VRMS, is it? So that will be equal to 220 multiplied by root 2 volt. This is V naught peak value, and that's all given. And 50 hertz. Find the amplitude of current in steady state, obtain the phase difference. Okay, so these all same thing like we have seen in the last part, and I can calculate it straightforward easily. Amplitude of current, so I know the amplitude of potential drop, amplitude V naught is this. For amplitude of current I need impedance means Z, and Z is equal to under root R square plus XL square. So R is directly given, it's 11 ohm. We need XL, and XL is equal to omega times what? Omega times L, and omega is 2 pi into F. F is equal to what? It's 50 hertz multiplied by L is how much? 35 into 10 to the power minus 3. This is will be in ohms. So now we can simplify it, and actually like pi can be substituted as this is 22 by 7. So solving it we will get this is exactly 5. This is 5 into 10, 10, and this like, so solving we are getting XL is exactly equal to 11 ohm, right? So we got XL. Then what is Z? Impedance is given by under root 11 square R square plus XL square, 11 square, that is 11 under root 2 ohms. This is your Z. Now A part or first part, it's talking about the amplitude of current in steady state. So amplitude of current can be expressed as amplitude of current that I naught is equal to V naught divided by Z, and V naught is 220 root 2 divided by 11 root 2, and we are getting I naught is coming out to be root 2 gets cancelled, and it's 10 ampere. So I hope you understood how we exactly approach this way. So like we got this part, obtain the phase difference between current and voltage. Phase difference we know also. So phase difference, and that is given by phi is equal to tan inverse of XL by R, and this is equal to tan inverse of XL is 11 divided by R is also 11. This implies phi is equal to pi by 4. So we got the phase difference, and we know actually in case of LR circuit our current lags behind by angle phase, and phase is given by pi by 4, right? So that is also done. Now phase difference between current, and also plot the variation of current and source voltage. So that plot can be done. This is your source voltage is V naught sine of omega t, so we can write V naught sine of omega t is equal to this for one cycle. And now it's talking about like here it's lagging behind, current is lagging behind by phase angle of pi by 4. So it will be starting from like this is pi by 2, this is pi, 3 pi by 2, and this is 2 pi. So it will be starting from here, like because current is lagging behind by some phase of pi by, and its amplitude will be also 10. Here amplitude is 2 root 220, is it? So this peak value, this will be 220 root 2 voltage, but here the value of current, it will be something like this. It's also exactly like sine. We can write I can write is equal to 10 sine of omega t minus pi by 4. So it will be exactly same thing, same function, but it will be shifted by a phase of pi by 4. So that will be, so this will be your current starting like this. It will be something like that. So this is I variation and this is V variation, and this is all about problem. So I hope you should not find it difficult at all. This is what exactly we have discussed in the last part, and if you just understand the concept, simply go through it, apply it, things will be straightforward, not at all complex. Let me continue with the next part, that is like we finished that LR circuit. Let's say next CR circuit or RC circuit. So let me first erase it. Okay, so next here we have series RC circuit. Whatever you can imagine in case of, or imagine from your LR circuit part, exactly same thing we are supposed to find for this case also, and the approach will be also exactly same way, only the calculation part and the answers will be different little bit because the case is different. It's series RC circuit and that was exactly series LR circuit, so that's why, but the approach will be still same. So here first thing is like resistance, you can write simply R, and for capacitance we'll write its capacitive reactance. Capacitive reactance, we have already seen what it means. It's denoted by XC, and that's given by 1 by omega times C. Clear? This is 1 by omega is 2 pi F times C. This is XC. In this case again, here we have R and C, two circuit elements that two connected in series, right? So what we will do is we will write phasor diagram, and which quantity will be taken on along x-axis. So the elements are connected in series, which quantity will be constant, that is current. So definitely on x-axis we will consider current, right? So here let's say this is a phasor diagram and I am taking here I along x-axis because it is in series. Now so VR will be equal to what? This is VR. Remember this is what? Peak voltage. So if I is the current in this element at time t, and I will add the peak value of this current also. This is the peak value of potential drop across resistor. Then across like capacitor, same current will be there, but in case of capacitor, what is the phase relation between current and potential drop? You must remember that, and that is here in case of capacitor, your potential drop lag behind current by a phase angle of pi by 2, correct? So that's why I will write the potential drop across, that is VC, this will be lagging behind the current by a phase angle of pi by 2. Clear? So here if I is the current, or I can write if let's say I naught is the peak value of current, is peak of current in circuit, then peak value of potential . difference across R and C can be expressed. So VR is equal to what? I times R, and similarly VC is equal to what? I naught times XC. Clear? So that is what we can write. In the phase relation, I got this. So the net potential difference, net EMF will be across what? This is your V, and this V will be along this way, right? Net EMF here comes in the direction or along the source EMF. So here this is my source EMF. This like peak value can write V naught, and this V, if you write, then it will be V naught sine of omega t. So the phase of this potential drop will be this one actually. So now you can see the current in this situation, in this case, will be actually leading your potential drop or your source EMF by an angle again phi, and here I can get easily phi. So first like I can calculate here, V naught is equal to what? Under root VR square plus VC square, what I have written, yes, exactly, and this can be expressed as under root, this is I naught square into R square plus I naught square into XC square. This comes out to be I naught under root R square plus XC square. Clear? And again this is equal to what? My peak voltage, and here I write under root R square plus XC square. This is Z, and that is called impedance of RC circuit. So I got the peak value of current, the of current I naught is given by V naught peak value divided by Z, or V naught divided by Z is under root R square plus XC square. This is the peak value of current, we got it, and these are the peak values. So once you have peak value of current, you can substitute here, you will get VC and VR also. Next thing is, already I am having, can I get current as like a function of time? So first let me say here for RC circuit or series RC circuit, you can write here current lead voltage by phase angle phi, and phi can be expressed as what? So we can write 10 phi, either you can write it this way. I'm directly writing the magnitude, automatically it's taken downward actually. So from, you will write it with respect to this, then I will be like added. If you're writing with respect to I, then here it will be subtracted. Okay, remember that. So here 10 phi, I'm just writing the magnitude, it will be equal to what? VC divided by this VR, or you can write this is VC divided by VR, and VC is what? VC is this. VC is I naught into XC. So and this is VR is I naught into R. I naught gets cancelled. This comes out to be what? This is XC divided by R. This is phase difference phi. So the phi is known, then I can get my current. So I is given by I naught sine of omega t plus phi or minus phi. It should be plus phi, because your current will be leading the potential drop, the source EMF in case of RC circuit. So I hope things are straightforward. There should not be any confusion anywhere. Like, you need to just remember things. You need to like keep the things in mind, that how we draw the phase diagram, which things we should draw along the x-axis, what exactly each term means. That should be clear to everyone. So I can write it properly more. This is I naught is V naught divided by under root R square plus XC, under root R square plus XC square multiplied by sine of omega t plus phi. And phi is, remember this, so this is the expression of current in this circuit. Now you like, so current will be same in across R and C. Now I can get these are what peak values, but if I need the instantaneous potential drop across resistor and inductor, that also I can express. So the instantaneous potential drops across R and C, that can be written as VR is equal to what? I times R, and I is this, so this comes out to be V naught R divided by under root R square plus XC square times sine of omega t plus phi. So this is your potential drop across resistor function of time. I hope you are getting it. Again, I am telling you, potential drop across resistor will be in same phase with the current across resistor, but it's not necessary that the phase of potential drop across the resistor will be in same phase with the source EMF. That is not compulsory, not necessarily true. Maybe that depends on the situation, just like it happened in case of purely resistive elements. So that is the situation. So here similarly I can write potential difference across capacitor. So capacitor current I got exactly this. What about the potential drop? Potential drop in capacitor lag behind its current or current through the capacitor. So current through the capacitor is given by this. Peak value of potential drop across current like capacitor is given by I naught, its peak value multiplied by XC, and it will be like I naught I got, so this, then I will get a function of time, but this like current through the capacitor is exactly that. If I multiply this, I will get peak value. Well, how I will get calculate phase? So phase of VC is lagging behind IC by pi by 2. So by considering all these factors, I can write VC is equal to I naught, that is V naught divided by under root R square plus XC square multiplied by XC into sine of omega t plus phi. This is the phase of current, but VC is lagging behind current by phase angle of pi by 2, so it's minus pi by 2, and this is your complete expression. So whatever the expression, whatever the relation you are asked to find, I don't think you should have any problem in any part of this like a series RC circuit. Let's see some application of this part also. Okay, see next application, next problem that is based on RC, series RC circuit. Just to study it. So a 200 ohm resistor is connected in series with, so this is about RC circuit, 200 ohm. This is, let me draw it first the circuit. So it's a 200 ohm resistor connected across 5 microfarad capacitor RC, and this is V naught, V is equal to some V naught sine of omega t. This is not given actually, and maybe some plus some phi naught, so nothing is given about it. So here the voltage across resistor, across this it will be VR, and this it will be VC. A is given, so R 200 ohm, C 5 microfarad, VR is 1.20 volt into sine of 2500 into T. This, and now it's asking derive an expression for this circuit current. Okay, so just read the problem and think about it. I think you can easily get the idea that how we will approach this problem. So here things are a little bit twisted. Here instead of giving you this information directly, it's you are provided with this potential drop or instantaneous potential drop across resistor, then you are asked to find Vc and remaining things actually. So how we can find? So definitely the current in this complete element will be same, right? And if I is the current, then what I can write? Let's say if I is the current in circuit, then I can write VR is equal to I times R, and it will be like you can write like peak value in the phase of this I will be same as phase of R. So phase means this quantity will be same, only this quantity is VR, and that I can write. So this is equal to 1.2 volt, and that is equal to I naught, I don't know, and R is equal to how much? 200 ohm. So I got this implies I naught is equal to 1.2 divided by 200 ampere. Clear? Once I got I, then I can write what is the circuit current. So the current in the circuit can be expressed I is equal to 1.2 divided by 200 and multiplied by, this is a phase will be same, sine of 2500 t. This will be, and you can further simplify it, so it will be like 0.6 divided by, so this is 0.6 into 10 raised to power minus 2 sine of 2500 t. This is the circuit current as function of time. I hope you understood this part. Next, B part, determine the capacitive reactance of the capacitor. So it's talking about Xc, and that is equal to 1 by omega into C. And we are provided everything. Omega is 2500, C is given as 5 into 10 raised to power minus 6. So you will get it 10 raised to power 6 divided by 2500 multiplied by 5. So it's 10 raised to power 4. If I just cancel these two zeros, and 10 raised to power 4, so you can write it 100 into 10 raised to power okay, let me write it simply, 25 multiplied by 25. So this is how much? 4. This is how much? 2. So we are getting Xc is equal to 80 ohm. Clear? And the next part, derive an expression for the voltage across capacitor. So first I need to find that C part. So Vc naught means peak voltage across capacitor. That is given by I naught multiplied by Xc, and I naught is 0.6 multiplied by minus 2 into 80, and this comes out to be 4.848, so it's 0.48 volt, and then the voltage across capacitor actually lags behind current by a phase of pi by 2. So this implies I can write Vc is equal to 0.48, and that is 1.2, that's right. So the 0.48 multiplied by sine of omega 2500 t. This is what? Phase of current, circuit current, but current like voltage across this will lag behind the current by a phase of pi by 2. So that's why lag behind, so means I need to write minus pi by 2. So this is your part C. So I think it's just, you need to think a little bit and you need to think logically, then it's just straightforward things. I don't think you should have any problem in solving this type of questions. So this is about RC circuit, and the last part, next part is series LC circuits. So let me talk about that. Okay, so let's talk about the next case, that is series LC circuit. So here inductor and capacitor are connected in series across a power source, alternating power source. This is V equal to V0 sine of omega t. This is L, this is C. I cross this VL, this is VC. So exactly the same as what we did for a LR circuit and RC circuit. Similarly, we are supposed to do the remaining things like exactly same things for this part also. So again, let's say VL and VC are what? Like peak voltages across inductor and capacitor. So first thing is, like right here we have only what? There is no resistor. So this complete circuit will have reactance, no impedance. I mean, like impedance we can say will be equal to reactance. There will be no resistance. So here I can write capacitive reactance XC is equal to what? This is 1 by omega C. We have omega and C. So this is XC. Similarly, inductive reactance, I can write XL is equal to omega times L. So we got this. Now in this situation again it's in series, so things will start from the phasor diagram. So here let me say the current in the circuit is I, and I am taking this current I along X axis. Okay, and if I take it I0, then it's the peak value of the current. Okay, so this is the current in the circuit. Now let's talk about inductor. So potential drop VL across inductor will be like what? How the phase of VL will be related to I, current through it. So you must be remembering that phasor, like the VL potential drop across inductor must be leading the current through it by a phase angle of pi by 2. So that's why I can write VL will be here up, and the same current will be passing through this capacitor also. But potential drop across capacitor actually lags behind like this I, so I will write this will be pure VC. Now depending on these two parameters and like L and C values, either VL will be greater or maybe VC will be greater. So according to that, like overall the circuit will be either behaving like as a capacitor effectively or maybe as an inductor, depending on which quantity is higher. Is it? So first thing is I can write VL is equal to I naught into XL, VC is equal to I naught into XC, I naught XC. Clear? And here the voltage V, I will write actually phasor diagram because these two are in opposite signs, so I will write it's equal to VL minus VC. Here, if VL is supposed to be greater than VC, vice versa, it will be V will be equal to VC minus VL if I take VC is greater than VL. So either way, same thing. So this I can write here. Then I can write V is equal to I into XL minus I naught into XC, and that is I naught into XL minus XC. Here, so here XL minus XC, you can write it's the like X, or you can write it also at Z. So here simple like impedance I can call it, actually it will be the reactance of the circuit is given by, I can write it simply X. The reactance of the circuit is the difference of like whichever the reactance is dominating minus the other. So here like this is the situation, and here we got everything like this, and what will be the current in this situation? So the current peak value of current through circuit this can be written as I naught is equal to what? This is V naught divided by XL minus XC, right? And this is XL minus XC is I naught, and I can write I. So net current will be what? Here this is your net EMF. Now if this is the condition, then net EMF will be, this will be along this. In that case, your current will be lagging behind, is it? So here I will write this: if VL is greater than VC, the circuit will behave like purely inductive circuit, and similarly if VL is less than VC, the circuit will behave like purely capacitive circuit. Clear? So here that is the thing. Now I can write VL minus VC. So here if like this is the condition is taken, let me write the things according to this. In that case it will be like inductive. In case of inductive, this net EMF will be across this, and so current will be lagging behind, is it? So if that is the condition, then current will be lagging behind V by power. So I can write I is equal to V naught divided by XL minus XC into sine of omega t minus pi. Similarly, if it is net capacitive circuit, then you will write V naught by XC minus XL sine of omega t plus pi. So this is about series LC circuit. So first thing is, if purely capacitive, resistive, inductive circuit is given, AC source is applied, whatever is asked, you must be in position to answer that. Similarly, like either LC, LR, RC circuit is given, and one AC source is connected across them in series. Like elements must be connected in series. Then in that situation also, like anything is asked to you, you must be able to answer that. Here we are left with one more thing actually, and before going for the next series LCR circuit, means when all three elements are connected in series. I will also talk about the case when all three elements are connected in parallel. In that situation, how we calculate current, potential drop across each element, and before that I need to calculate power dissipated in AC circuit. So let me first talk about that after this. Okay, so let's next talk about power in an AC circuit. So up to now, like we understood that whatever the situation, or mainly we can say it's about like when series RC, RL and LC circuit, or simple purely inductive, resistive and capacitive circuits is given. So in such cases, if some input power, alternating power is provided, then we can get the current. So in any circuit, in general result, I can write, let's say this is a box containing some circuit elements, and like both this complete system is connected to a battery. So V is equal to some V naught sine of omega t, right? Then the current through this circuit I can write in general term, is it? So if V is equal to V naught sine of omega t is the power supplied, is it? Is the source voltage of AC source. Then depending on what is there in this box, which element is there in this box, in general term I can write current is equal to some I naught sine of omega t. It depending on either plus or minus, it will be some phi. So let me take it just phi. So now this is the current, you can say, which is being supplied by the current, so like this voltage source. So I can write current supplied by the source is simply equal to same current. So it's I naught sine of omega t plus phi. So now it's easy, like see, this is the potential drop of the source, this is the current supplied by it. So how much is the power supplied by the source, and exactly I can say the power supplied by the source will be like consumed completely. Instantaneous may not be, like I can write for average power, that will be exactly equal, that power supplied by the source will be the power consumed in the AC circuit elements cumulatively. So I can write now the power supplied by AC source. This can be written as power is equal to this, you can write V multiplied by I. Clear? Let me substitute things here. So power instantaneous is V naught sine of omega t multiplied by this is I naught sine of omega t plus phi. This is the net power. Now I can simplify it. So this is okay. So instead of V naught, because I have taken it most of the time E, let me write it in terms of E naught. E naught, and this is E. E naught is the peak value and so on. So now I can write this is E naught, E times V, and here I am getting this E naught sine of this. So this comes out to be E naught, I naught, and sine of omega t. This can be expanded. Right term sine alpha plus beta. So it will be sine omega t cos phi cos omega t into sine phi. Again further multiply it. It will be E naught I naught sine square omega t into cos phi plus this is E naught I naught sine omega t multiplied by here. So it will be sine omega t cos omega t into sine phi. Clear? So this is what instantaneous power. So the average right, I can write P instantaneous. This is E naught I naught sine square omega t cos phi E naught I naught sine omega t cos omega t into sine phi. The average power P average will be equal to what? Average of all these things. So that I can write average of E naught I naught sine square omega t into cos phi. To get the average of these quantities, like E naught I naught, it's constant, cos phi is also constant. I need to take the average of sine square omega t. So one way is you can go for integration for one like one complete cycle. Otherwise we directly know the average value of sine square theta is simply half. So I will be using that result. So, and plus similarly here I can write I naught E naught, let me write it 2, and this will be 2 sine omega t cos omega t, that I can write sine phi here, and it's sine of 2 omega t. So here also these quantities, this is constant, this is constant. Average of sine 2 omega t is also 0. So this implies average power, let me write it, AVG is equal to E naught I naught, because average of this is 2 1 by 2 and cos phi, and plus this quantity will be simply equal to 0. So this is the average power, and we can rearrange it. I can rewrite it. This is E naught by root 2 I naught by root 2 into cos of phi. So this can be also written as E RMS I RMS multiplied by cos of phi. So this is the average power consumed in an AC circuit. Now remember that ERMS, IRMS, we can calculate peak value divided by 2 into cos of phi. Phi is what? If you look at it from here, then phi is what? Phi is the phase difference between like source voltage and current through the circuit. So here you can write phi is the phase difference between source voltage and current through circuit. And here this cos phi is also called power factor. Cos phi, this is called power factor and it depends on the circuit, right? And how we will get cos phi? So I have already told you how to calculate phi depending on the circuit. It's purely inductive, capacitive, resistive, or RC, LC, or like LR, whatever the case is there. In every case, we have already got the relation for calculating phi. So that same phi will be this phi, and then cos phi will be the power factor, right? So this is how we can get simple term, nothing to worry about. We have supplied some power, whatever the circuit element is given to you, you can get the current through that, and automatically you will have phi also here, right? Because to get the current you need to calculate phi actually. So phi will be your phase difference between current like supplied voltage and the current flowing in the circuit. Then power, like we can supplied by the source, will be the power consumed in the circuit elements, that you can write E into I, potential drop multiplied by the current, and simplifying it and getting its average, we are getting this is the result, and that you can rearrange this way and this way. So P average is ERMS into IRMS multiplied by cos of phi, where cos phi is also termed as power factor of a circuit. So let me just give you some case, like when, in which case what will be the cos phi. So based on that I can also say that which element will be like consuming power and which case it will be not, right? So let's see. First case, purely resistive circuit. So you have already, you must be remembering it, what we have seen. This is VR and this is IR, depending on, maybe this is VR and this is I, means current through resistor. And you must be knowing that this is the phasor diagram for purely resistive circuit. So here, what is the phi? Phase difference is 0. So this implies cos phi. This is called power factor for purely resistive circuit. I can write power factor will be equal to what? Simply 1, because phi is equal to 0 if you substitute here. So power consumed average, this is given by E RMS multiplied by I RMS, that is also equal to E naught I naught divided by 2, because cos phi will be equal to, so yes, there will be power consumed and it's given by this relation in a purely resistive circuit. Similarly, if I talk about purely capacitive, then what will be the power in purely capacitive circuits? That will be equal to what? We will write purely capacitive circuits. So capacitive circuits, listen it. In case of capacitive, if this is I through the circuit, then VC is down, because VC lags basically your I through the circuit or capacitor by a phase angle of 90. So what this phi is what? Phase difference between current and potential drop or voltage. So I can write here, this implies I say current, this is the potential drop. See, there can be two things. If I am general given potential difference and current through some circuit element, power consumed in that circuit element I can calculate. Another way is if I'm talking about simply source, is it? So then source voltage multiplied with the current supplied by the source, I can multiply and I can get the power supplied by the source. So in general term, actually, like depending on the condition what it is asking, like I calculated the condition this, like that was power supplied by the source, but now I am calculating here the power consumed in a capacitor or capacitive circuit. Then power consumed in a capacitive circuit, when I am talking about, then I will be using power of voltage across, like a potential difference across the capacitor multiplied with the current passing through it. That will be your power consumed in capacitor. So it's nothing wrong. If I derive even the result, I will get exactly same thing. That will be the, like whatever the element it is, doesn't matter, potential drop across it multiplied by the current flowing through it will give you the power. right? So exactly same way. So here if I, and this is the VC, potential drop across the capacitor, then I know the potential difference between these two is 90 degrees. So here I can write phi will be what? 90 degree, and this implies cos phi will be 0. So power factor of purely capacitive circuit, power factor is equal to 0, and this implies if power factor is equal to 0, and that implies your power, average power consumed, will be I RMS E RMS into 0, that is 0. So means a purely resistive capacitive circuit is not at all a dissipative circuit. It will store some amount of energy for half of the cycle or some part of the cycle. In the next part it will release actually. So it is simply storing, releasing. Ideal capacitor, it does not dissipate energy. Yes, here I am talking about ideal capacitor. There may be situation like if we talk about real capacitor, then definitely some resistance will be there. In that situation some heat or some power get lost actually. So this is the condition for purely resistive circuit, purely capacitive circuit. In that case there will be no loss of power. So wherever like doesn't matter whatever the type of circuit it is, if power factor of a circuit is 0, that means there is no power consumed, no average power consumed in the circuit. So similarly let me show you here third case for purely inductive circuit. Purely inductive circuit. So in this situation, this is purely inductor connected. So like here I can write whatever the potential drop across this is okay, I can write. So potential here it will be VL and this is IL. So here also you can get the phase difference between L, potential drop across inductor, and current passing through it is having like phase difference of 90 degrees. So here also phi is given by 90 degree. That implies cos phi is equal to power factor, that will be equal to what? 0. So average power consumed is equal to E RMS into I RMS multiplied by 0, and that comes out to be 0. So there is also no average power supplied in case of purely inductive circuit. So it also does not listen my things carefully, is it? Focus on every word is important, because whatever I'm saying here, it's talking about average power. So if I in a cycle, if I say how much is the energy power consumed by the inductor, the answer is 0. If I just talk about at some moment power consumed in the inductor, it will not be 0, it will be something actually. But in some part, like it will be absorbing, in another case it will be supplying. Overall in a cycle, if I look at it, then power consumed in the inductor will be 0. Getting it? So that is, so this is for purely inductive circuit. Depending on if I am given, let's say LR circuit, is it LR circuit? So in this situation we already know LR. This is what? Series circuit, I through the like circuit. This is VR, this is VL. So we know V is net given by this, and there is phi. And in that situation we calculated tan phi is equal to what? It's VL divided by VR. VL we write I into XL, VR we write I into R, and I gets cancelled, this comes XL by R. So this is tan phi. So here what I can write, cos phi is also equal to what? Cos phi will be like base divided by this, and that will be, you can write R divided by Z, because this will be your Z, and that is under root R square plus XL square. So this is your cos phi, some power factor. Now if I get I peak value or RMS value, I get the net value, peak value or RMS value of potential drop, then I can write power consumed here power, average power is equal to simply E RMS multiplied by I RMS into cos of phi. So you can see here your cos phi power factor is not 0, so definitely in this element there will be power consumed. Is it? Let me just show a little more calculation for this. Okay, listen it. For this case, I can tell you it in different way. We will get same result also. This is our LR circuit, I current, power battery source connected. So we know already I like in the circuit, if I am taking it along x-axis because both are connected in series. So let's say if I is that, VR will be in same phase with I, and VL will be like leading by this I by 90-degree phase. So I can get tan phi and cos phi and current in the circuit, because your current will be lagging voltage, so that will be like sin omega t minus phi. So here the phase difference is between current and the like voltage supplied is exactly phi. So total power or average power supplied by this battery or by this source to this circuit element, I can write, so P, is it instantaneous, it will be simply this multiplied with that. So here it's exactly like I will write this as, let's say, I naught. So this is E naught, I naught. Exactly by doing same way I can write it is equal to sin omega t minus phi into sine of omega t. If I do the calculation part and getting average, then it comes exactly E naught into I naught divided by 2 into cos of phi. So the relation will be, I will be getting exactly this way even if I am going step by step. Now this E naught is E naught, I naught is this, so it's multiplied by E naught divided by what, under root R square plus XL square, this whole divided by 2, this multiplied by cos phi. So cos phi is how much? Cos phi is this, and that is R divided by under root XL, R divided by, just wait 1 second, this multiplied by cos of phi. So this coming out to be, cos phi is here R divided by R square plus XL square. Clear? Now I can multiply it. So this is coming out to be E naught square into R divided by 2. This is R square plus XL square. So this is the average power consumed in an LR circuit. So I think like by this time you must be clear that how to calculate the average power or power consumed in any circuit element, LR, RC, whatever the case it is there, we need to calculate power factor. That is quite important to get the power consumed or power supplied in the circuit. And we must have ERMS, IRMS, then it's straightforward, just substitute the result, you will get the answer. So this is all about power in an AC circuit.